Students, you have learned differential equations earlier and have learned to solve differential equations, and you have learned that differential equations has got solutions in the form of functions, but it is found that some differential equations cannot have a function as its solution. So usually we have it like this: y is equal to e to the power c1 e to the power mx, or c2x, or something else, sin x plus c2 sin x, or x square sin x. We usually have it in this manner. But then there are some differential equations for which you can't find solutions of this type. We don't get an exact function. So in such situations, what we do is we try to find an approximate solution. An approximate solution in the form of an infinite series. So there are different physical problems where the series, this infinite series, is found to be a very good approximation. So this type of solution is very much of use in, especially in physics. So we are going to do today's series solution of differential equation. So for the next few classes, we will be doing series solution of differential equations. For this, we must familiarize ourselves with a number of things, a number of ideas. First, let us see what are ordinary and singular points of a differential equation. Points of a differential equation. So let us consider an equation like this: y double dash plus px y single dash plus qx into y is equal to 0. Let us consider this. Let this be equation number 1. Obviously, this is a differential equation of the form d2y dx squared plus px. What is px? It is some function of x, dy by dx, plus qx is another different function of x into y is equal to 0. So this is a very common type of an equation. So this is of this form, and I'm just taking this as an example. I'll try to define what are singular and ordinary points. So now, if x is equal to x naught, x is a variable here and x naught is a particular variable, maybe 2 or 1 or 0 something. So the x naught is a particular value taken by x. So if x is equal to x naught, I shouldn't have written here x. If x is equal to x naught is called an ordinary point, of equation 1 if both px and qx are analytical analytic at x is equal to x naught. So I'd just like to remind you what we mean by analytic. So I'm sure you must have got the word analytic. So it's like this. So we are going to explain, not explain actually, I'm just going to remind you what is an analytic function. So analytic function I'll give you the definition. A rational function is analytic everywhere except at those values of x where its denominator is 0. Let us look at an example and try to understand this. Denominator is 0. So let us look at a function f(x) which is equal to like this, which is equal to x divided by x squared minus 3x plus 2. So here I can factorize the denominator, and then this becomes x minus 1 and x minus 2. So you see, when I put the value x is equal to 1, this denominator becomes 0. So the function becomes x by 0, which is infinity. Again, when I put x is equal to 2, the same thing happens, and the denominator becomes, let's see, its denominator becomes 0. For other values of x, we don't get it 0. So that means the function is not analytical at x is equal to 1 and at x is equal to 2. At other points, all other points, it's analytical. So you see, even let's take some other function. Suppose f1x. f1x is equal to, suppose sin x divided by x plus 4 whole square. Look at this function. See, when I put x is equal to minus 4, so the denominator becomes 0. So x is equal to minus 4, this second function, this which I have written as f1x, is not analytical. So if I know what is not analytical, I can easily say that which gives the denominator non-zero, that is analytical. Actually, being analytic has got other definition. It's analytic, not analytical. So it is analytic function, and why I am using this particular definition is because this will be used in our main aim, that is to find ordinary and singular points of a differential equation. So we come back to what are ordinary and singular points of a differential equation. So we had a differential equation y double dash px y single dash plus qx y is equal to 0, and x, if x is equal to x naught is an ordinary point, then both these functions of x which are multiplied to dy by dx and to y, they are analytic at x is equal to x naught. That means they are non-zero. So this is the definition of an ordinary point. Things will become clearer when we will find ordinary points and singular points for differential equation when we will start doing numericals. For the time being, let's just look at the definition. And now what happens if it's not ordinary? If x is equal to x naught is not ordinary, then what happens? Is not an ordinary point, not, I shouldn't say ordinary, not an ordinary point of the differential equation which I have named as 1, then it is called a singular point. That means if the denominator becomes 0 at when I substitute x is equal to x naught, then x is equal to x naught is a singular point. Then singular point are again of two types. So we have singular points. So singular points are two types. And what are they? They are, number 1, regular singular point, and number 2, irregular singular point. Now what are these irregular and irregular singular points? Let us see. So first let us also remember the equation that we had written as equation number 1. It was y double dash plus px y single dash plus qx y is equal to 0. This was a differential equation and we had named it 1. If both x minus x naught into px and x minus x naught whole square into qx are analytic at x is equal to x naught, then we call that, then